For 200 years, a certain type of math problem was basically locked in a vault, officially stamped unsolvable. It was a closed door in the world of mathematics. But what happens when someone claims they've finally found the key?
And that's the big question we're digging into here. We're going to look at a mathematical theorem that was considered settled law and a completely new way of thinking that claims to just, walk right around it.
So, to really get why this new approach is such a big deal, we first have to understand the lock. Let's rewind the clock almost exactly 200 years. Way back in 1824, a mathematician named Niels Henrik Abel dropped a bombshell with a landmark proof. He showed that while you can find a general formula for equations up to the fourth degree, anything higher, impossible. And for 2 centuries, that was just accepted mathematical fact, until 2023, when this new symbolic method was introduced by Murad Sultan Azawi. And listen, this wasn't just some small roadblock. As the source material puts it, Abel's work literally closed the door on the possibility of exact formulas. For generations, mathematicians had to fall back on approximations, which, always come with rounding errors and can get unstable. The perfect, exact answer was thought to be forever out of reach. But here's where it gets really, really interesting. It's all in the fine print. Abel's theorem is incredibly specific. It says there's no general solution in radicals. Now, think of radicals as your basic math toolkit. Square roots, cube roots, that kind of thing. The theorem basically said you can't build the solution using only those tools. The impossibility only holds if you stick to that specific toolkit. And that, right there, brings us to the new framework. See, this isn't about breaking the old rules. It's about inventing a whole new game with a completely different set of tools. So how do you solve the unsolvable? Well, you don't break the old rules, you just play a different game. Abel's theorem was all about radicals. Azawidi's framework, it just sidesteps them completely. It uses a whole new symbolic language built on things like recursive power sums and complex exponentials. You don't need to be a math whiz, just think of it like this. Instead of using simple hand tools, this new method is like using a programmable 3D printer, building the answer piece by piece in a much more sophisticated way. And this chart, wow, it just lays out the difference in power so clearly. Classical methods, they hit a brick wall at degree 5. They have to rely on approximations that are always a little bit off. Azawidi theorem, on the other hand, claims to work for any degree, spitting out exact symbolic answers with absolutely zero error. It's a huge leap from close enough to perfectly precise. Okay, so how does this thing actually work under the hood? Let's take a peek at the engine driving this method without getting totally lost in the weeds of the formulas. It really boils down to a super systematic 3-step process. First, you just grab the coefficients from your original equation. Easy enough? Second, you run them through a special recursive formula. Now, recursive just means that each step's result feeds into the next one, kind of like a chain reaction. This calculates a whole new, much cleaner set of coefficients. Finally, you use these new, clean coefficients to build the exact answer. The secret sauce here is really this idea of structured recursion. Think of it like you're building something really complex, but with simple repeating steps. Each step is perfectly precise and builds flawlessly on the one before it. It just doesn't leave any room for guesswork or those pesky rounding errors to sneak in. All right, the theory is one thing, and it sounds amazing, but does it actually work in practice? Let's see what happens when we throw a monstrously complex challenge at it, a 19th degree polynomial. And here it is. Just look at that thing, a polynomial with 20 terms going all the way up to the power of 19. Using classical methods, finding an exact symbolic solution for this beast is precisely what Abel proved was impossible. So the method gets to work. It starts churning through the calculations to find those new symbolic coefficients. The first one gets calculated, and it simplifies down to a nice, clean 0. Interesting. Then it moves on to the next step, for k equals 2. The result? 0. Again. And for k equals 3, you guessed it, also 0. You can start to see a pattern emerging as the method just systematically carves away all the complexity. The process just keeps going, 0, 0, 0, until, bam! At step k equals 8, something happens. Suddenly, our first non-zero value appears. We've got our first key piece of the puzzle. So the process keeps on chugging along, searching for the next piece. All the terms in between, they all simplify to zero, until another critical value pops out at k equals 17. And now we have the two main components we need.
And here is the beautiful result of all that heavy lifting. Almost all of the new symbolic coefficients are zero. They just vanished. Only two of them, s sub 8 and s sub 17, actually have a value. This is that breakthrough moment where overwhelming complexity just transforms into elegant simplicity.
And because all those other terms went to zero, that absolutely terrifying 19th degree polynomial collapses into this much, much simpler form. What looked like an impossible monster is suddenly something we can actually work with. And with that incredible simplification, the path to the final answer is totally clear. The impossible problem has been tamed, and now we can actually construct the exact solution. And there it is, an exact symbolic formula for every single root of that massive 19th degree equation. You can see how it's built right from those two key non-zero values we found earlier. No approximations, no rounding errors, just a perfect, precise answer to a problem that was considered unsolvable for 200 years. So, a 200-year-old problem gets a brand new, exact solution. That's cool. But what does this actually mean, beyond the world of pure mathematics? Well, this is way more than just a clever math trick. First off, it gives us a way to get perfect precision, which could make numerical guesswork obsolete for these kinds of problems. Second, it's a tool with zero rounding error, which is absolutely critical in fields like physics and engineering. But maybe most importantly, it's a really profound statement about the very nature of impossibility. What we think is impossible is so often just a limitation of the tools and perspectives we're using at the time. It really makes you wonder, doesn't it? By changing the rules and inventing new tools, a door that was locked tight for 2 centuries was finally bypassed. It just begs the question, what other impossible problems are out there, just waiting for someone to find the right key?